We're not just talking about faster Wi-Fi, we're talking about building an actual internet that stretches across the entire solar system. That might sound like science fiction, but it is already becoming a structured, strategic project with real missions, hardware, and timelines. From SCIFI idea to serious plan. Extending the internet beyond Earth has shifted from an imaginative concept to a concrete engineering goal, and Europe is taking a leading role in turning it into reality. Earlier this year, a major study was completed that sets out how Europe could help create what may become humanity's first network spanning the whole solar system. In May 2024, a dedicated study was commissioned under a European preparation program to define what a solar system internet, ESSI, should actually look like in practice. The study described SSI as an operations-ready communication and navigation backbone that could support many future missions instead of each mission having to build its own bespoke links. To tackle this, a German-led consortium was formed, bringing together several specialist organizations with clear roles. GMV took charge of project management and systems engineering, Novaspace focused on strategy and long-term roadmaps, and D3TN concentrated on communication protocols and governance questions. This kind of division of labor is essential, because building an internet for space is as much about policy and standards as it is about antennas and lasers. A leading figure in this effort, Felix Flentger from the Directorate of Operations, described the long-term ambition as establishing a solar system internet that supports advanced deep space radio and optical links, as well as positioning, navigation, and timing, PNT, services. In simple terms, that means not only sending data, but also helping spacecraft know where they are and what time it is with high precision. Why a solar system internet is so different. On Earth, the internet quietly relies on conditions we take for granted: quick two-way connections, fairly low delays, relatively stable networks, and small error rates. Your messages usually bounce back and forth in fractions of a second, and the underlying infrastructure rarely moves. Space blows all of that up. A solar system internet must cope with constantly changing network layouts as planets move, very long delays, minutes or even hours for distant destinations, more frequent errors, and tight limits on both energy and bandwidth. Signals can be weak, links can disappear behind planets, and hardware must survive harsh conditions for many years. But here's where it gets controversial. Should we try to imitate the Earth internet as closely as possible, or do we need something fundamentally new for space? To handle this environment, the consortium identified three main technology pillars that everything else will rest on. Think of these as the core foundations: a way to move data reliably despite delays, a way to push huge amounts of data over vast distances, and a way to know position and time accurately far from Earth. Pillar 1. Disruption Tolerant Networking, DTN. Disruption Tolerant Networking, or DTN, is the heart of the solar system internet concept because it is designed for unreliable, delay-prone environments. Instead of assuming a smooth, always connected path, DTN uses a store-and-forward approach. Nodes hold on to data until a link opens up, then pass it along step by step. This means that even if a spacecraft drops out of contact for a while, information is not lost. It simply waits at an intermediate node until the next chance to move. It is a bit like mailing a package via several post offices that temporarily close and reopen. The system is built to tolerate those gaps. DTN is not just theoretical. It has already been demonstrated in real-world trials involving multiple partners. One notable example is the Lunar IceCube experiment, where a ground station in Kourou worked together with NASA's Jet Propulsion Laboratory and other teams to show DTN in action for a lunar mission. These demonstrations are early proofs that the basic internet logic here for space is feasible. Pillar 2. High-rate optical communications. Radio links have carried most space data so far, but optical communications, essentially using lasers for data transmission, are becoming crucial for deep space missions that need to send back huge volumes of information. Light-based links can pack far more data into a single connection than traditional radio systems, provided the pointing and alignment are extremely accurate. Recent mission tests have shown just how powerful this technology can be. On one deep space mission, data was successfully sent at tens of megabits per second from over 200 million kilometers away, showing that high-rate optical links are workable well beyond Earth's immediate neighborhood. Earlier lunar experiments achieved hundreds of megabits per second from the Moon, hinting at what future science missions could do when imaging planets, moons, or even asteroids in great detail. And this is the part most people miss. These laser links are not only about downloading pretty pictures faster. They can also reshape how missions are designed, enabling more autonomy, real-time decision support, and entirely new types of instruments that would have been pointless with slower links. Pillar 3. Deep Space PNT. Positioning, Navigation, Timing. On Earth, navigation is now almost synonymous with satellite navigation systems, which provide extremely accurate position and time information. For deep space, something similar is needed, but it has to work far beyond the range of terrestrial constellations. To deliver PNT in deep space, the system will rely on highly autonomous orbit determination and time synchronization, ODTS, methods. That means spacecraft and infrastructure nodes must be capable of figuring out their own orbits and keeping clocks aligned without constantly phoning home. Long-range optical and radio ranging techniques will help measure distances and relative positions across millions or even billions of kilometers. This may sound straightforward, but here is where opinions can diverge. Should deep space navigation remain tightly controlled from Earth, or is a shift towards semi-independent navigation networks around the Moon, Mars, and beyond both inevitable and desirable? Building on existing European infrastructure. The vision of the Solar System Internet is not starting from scratch. It builds upon an existing ground and space infrastructure that already reaches far into the solar system. A core network of deep space ground stations, including several 35-meter antennas, currently provides communication support for missions across a wide range of destinations. On top of that, Europe helps coordinate a Mars relay network through the European Relay Coordination Centre, ERCO. This network is already serving as the first operational interplanetary relay system, allowing different MICE spacecraft to parse data through each other instead of each mission needing a direct line back to Earth at all times. The longer-term SSI concept aims to integrate all these separate elements, and future ones, in a way similar to how today's terrestrial internet ties together thousands of independent networks. Instead of isolated mission-specific systems, you get shared infrastructure that many actors can use. Key programs feeding into the SSI. Several European programs are expected to become major building blocks of the Solar System Internet, each with a specific focus but designed to interconnect in the future. Together, they cover lunar, near-Earth, and Mars-related needs, as well as high-capacity data transport. Moonlight is set to become Europe's first commercial-style telecommunications and navigation service beyond Earth, focused on the Moon. It plans to use a constellation of satellites in special frozen elliptical orbits around the Moon to provide communications and navigation coverage for landers, rovers, and future infrastructure. HYDRON is working on a high-throughput optical space network capable of handling terabits of data per second, vastly exceeding today's typical satellite systems. This kind of capacity is key if space becomes crowded with data-hungry missions, commercial services, and scientific observatories. MACONI, short for Mars Communication and Navigation Infrastructure, is aimed at providing long-term communication and PNT services around Mars. The idea is to gradually assemble a multi-node constellation, supported by a propulsion-at-tug concept called Lightship, with the goal of having about 6 nodes in place by the 2040s. Here is a simple overview of how these initiatives relate to the Solar System Internet vision. Program Main Focus Area Role in Solar System Internet. Moonlight Moon Communications and Navigation acts as the first off-planet telecom and navigation provider for lunar users. HYDRON high-throughput optical link supplies ultra-high